quantum computers with spectroscopy. Please welcome on stage Dr. Jan Reiner.
Thanks. All right, hi everyone. So yeah, the title is shown, right? A bit bold at the beginning, exponential advantage, potential applications for quantum computers within spectroscopy. I was already introduced, Jan Reiner. This is a use case that we worked in collaboration with Merck on. And for those who don't know, HQS is a Karlsruhe-based startup that, well, by now has acquired roughly 40 employees, which, as was mentioned, I co-founded during my PhD. Right? Oh, okay. So what are we doing here, right? We have the quantum computer. We know, at least in abstract terms, there is some quantum advantage, right? At least, you know, particularly if you go to an error-corrected device, there are some things a quantum computer can do that a classical computer cannot do. So the key problem here is, of course, finding an application that is actually useful. And so this is what this talk is kind of about in this whole session. And I introduced this a bit because the proposals that are there are relatively scarce in the sense that there's not a large variety in the sense that many of them based on variational algorithms. And at HQS, we always had this question, okay, variational algorithms, what can they do, what can't they do? And when you look at it, it's of course very nice. It's easy to understand. You minimize the energy of some Hamiltonian with some parameterized state. Easy to understand. Relatively easy also to map to a large variety of problems. So that's really cool. Also, I won't say that variational algorithms are kind of out of the question. We do in fact think, and also research this, look at quantum machine learning applications where we also see that, okay, there might be actually some real benefit. In our case, what we do at HQS is the simulation of generally materials and chemicals. And here in quantum simulations, okay, there are a couple of questions that came up in some talks also here that people try to tackle, like, okay, the parameter optimization, right, Barron plateaus as a keyword, circuit depth, depending on your ansatz, it might be really hard, measurement effort, and so on. Also in quantum simulation, if you do these ground state calculations, the classical methods are actually really good. So you also have to be really, really good. So it might actually be beneficial to tackle a problem which classical computers cannot do so well. There's also an aspect that, okay, in the future, error-corrected devices, these variational algorithms are often kind of tailored to the NISQ error. The window is kind of closing, so it might also be, you might take a look into the future. For that reason, we decided to look into a different thing, something that quantum computers can really provenly do very well, which is the time evolution, because they are an artificial quantum system that time evolves when you do your circuit. The circuit in itself is really, really difficult to simulate, right? It's a dynamical problem. It encapsulates the excited states. This is something that's very hard for classical computers. And so there's a fundamental quantum advantage. So then the question really is, okay, what is the application then, if you would just want to do time evolution? And there's indeed practical use. So in an academic sense, correlation functions are interesting, right? If you talk to a physicist, they tell you, okay, correlation functions is nice. This is an inherited time evolution problem, but not directly an industry problem. Then what we also are concerned with is the fact that in a time evolution, if you know what the errors on your device do, you kind of can map this to an effect on the time evolution that you can understand, which is not necessarily the case for variational algorithms. And in fact, you can kind of mimic what you're doing with the evolution of an open quantum system, so a noisy quantum system. And you can understand this. And there are also a couple of recent works that also show that this is something which is not only usable or beneficial for NISQ devices, but also in the future it is something that the evolution of open quantum systems is something that is related to nature, problems in nature, and that this is still inherently very hard to solve. Oh, sorry, I skipped the actual part where I introduce Merck. The application where time evolution is really the core thing that we found together with Merck is NMR spectroscopy. So you might know this when you twist your knee and you have to go into the tube, and then they can look into your knee. All right, but in chemical industry, this is also used to analyze just molecules or substances, and this is a frequency spectrum, so the Fourier transform of a time evolution, right? It's really the key thing is time evolution. The question then is, can quantum computers help with that? So the industry relevance is just to say a couple of words about this. For example, if you set up a process, you want to kind of guarantee that you actually produce the thing that you want to produce, or you want to know in which quantity it is in there, and there's some solvent in there, and there's lots of going on. NMR is really a tool that is heavily used to do stuff like that, particularly in drug discovery. So if you can use quantum computers here, there is a market for it. That's basically what the slide is, I guess, supposed to say. So the question is, what part of this can you actually tackle? And for that, we also talked not only with Merck, but we did a lot of user interviews from people in the industry who use NMR. And what is currently done very often is you want to produce a certain substance, and then there's a reference spectrum, somebody measured it. And so you rely on a database. There's also classical methods to give you a spectrum, but depending on your precise machine that you do your measurement with and how the simulation is done, is also not quite clear if you can utilize this database and so on. So you might need to do this all yourself, and then, okay, there's tools for that, but this is then very time consuming and so on and so on. And there's also a key factor, which is the lack of accuracy, which is particularly true in something which is called low field NMR, which is a field that is kind of developing right now. So, I mean, as I said, the tube where you might, hurt yourself and have to go in. Very large thing. Actually does not even produce that high of a magnetic field, because otherwise your brain will start to warm up if you kind of go in, which is apparently not pleasant. But you need high fields to have a high resolution. And low field devices would, on the other hand, be very nice, because instead of having a huge device, you have something that someone on the lab has on his bench. Benchtop NMR is another keyword for that. So here might be actually a real use case, and I will talk maybe a bit more about this in a couple of slides. So yeah, since not only working on academic problems, but really figuring out what the industry needs. This was something that stemmed from actually a long collaboration with Merck, so it also took us a while to really figure out what are actually the details of it, to understand the problem and so on, and really built the whole workflow. We worked together with Merck since now roughly 5 years, and it's been really a great collaboration. And since we have that use case, we also contacted more people in the industry. There, however, I cannot share too many details. Apparently, pharma is quite a secretive field. But I just want to mention that generally this is something that is not only of academic context. Which is why we also chose this as really the central thing, or one of the central things, I would say, in our software offering. So quickly, the stage on which we present our software modules that we worked on, that we now sell, is what we call SQ stage. And there are, well, on the top right, top left, top right, bottom left, bottom right, there's highlighted these HQS molecules, correlator app, and spectrum tools as software modules within this whole offering that we have, which are specifically tailored to NMR. Generally, what we do is we have a lot of classical pre-computation. So let's say in this model analysis part, right, we do really industry problems. So it's beneficial if you're not a hardcore quantum computing expert to be able to do it, right? You kind of need to start with something that you're familiar with if you're in the chemical industry. So there's a lot of pre-processing, and this will of course always be needed. The quantum computer will not do everything. Then we have quantum computing part. This is to a degree tailored to academics or to people who want to understand the quantum computer, but also then as a backend, if you have created your model that you want to simulate. But then also we focus a lot on the classical simulation part, because there will always be at least parts of your problem that you will solve classically. Also, it's very important to use to also be knowledgeable about the classical, to how to solve the classical the problem in a classical way, because otherwise it's always difficult to judge whether or not this application actually makes sense for the quantum computer. And then on the top left, there's something we work on, which is basically that an AI tool that helps you kind of operate with our tools. Now the NMR use case, as I said, we have basically everything in our offering. You start with a molecule that you want to simulate, then there's a module which helps you to get from first principles the parameter that you need, and also calculating the spectrum either on the quantum computer or your classical device to get a reference spectrum for a certain molecule. So quickly touching on that, right, you really start with writing down your molecule. This gives you a structure. You can quickly analyze it. Is it the right rotamer, whatever, right? That you're also kind of sure that this is what you want to do. And also there's pre-computation for the parameters that you need to get your Hamiltonian that you want to solve at the end. And we are currently also in the middle of creating a then consistent database for molecules or parts of molecules, such that you don't have to do all the pre-computation always on the fly. Then there's spectrum tools. This is also something that we're very proud of. This is a cluster solver, which actually beats Spinach, which is an NNR solver, which is like the product that is out there. And even Ilya Kupov, the guy who is responsible for Spinach, said that he's remarked by our solver. Spinach, of course, has a lot of other things. The cluster solver is very important because it really dissects also a problem into smaller quantum mechanical pieces. So not only do we need this to understand the problem, to compare solutions, but also to prepare for the quantum computer. And then finally, there's also a quantum computing part where we can actually solve the Hamiltonians that we find on the quantum computer. And why is this potential quantum advantage? So what we found is that not all NMR problems are in fact something that needs a quantum computer. So you have basically, if you have a really large NMR device, you have large fields that kind of separate your individual spins in your spin problem very well. It only becomes a problem if you have either too many highly correlated spins, right, that you cannot really separate. So if you're using the cluster solver, you can kind of realize this, that, okay, I kind of need larger clusters because otherwise I cannot grasp the whole quantum mechanical issue. Or the other thing that I mentioned is this low field benchtop NMR, where you don't quite separate your spins that well because your magnetic field that separates them is too low, so you don't have quite a high splitting. Then the interaction between the spins plays a quantum mechanical role in the system, so you really need to treat a, let's say, 20+ spin system. I show here only a very small example, small molecule, it's a proof of concept more, where we showed it ran on an IBM device, an IonQ device, and in black in the background there's the reference calculation, the exact one. And currently we are trying to find a very nice use case to address also more hardware people, where we really have a problem of, let's say, the order of 20, 30 spins or something that's really, really hard to tackle classically, where we still have the solution, and then see whether or not the quantum computer can still reproduce the spectrum as well. The key thing maybe to highlight is that if we're using time evolution, even if we have noise, it is a scalable approach, because what it would do, right, for those who are as technical, it would broaden your spectrum. So this is something that you would expect also in the low field spectrum that you would measure. So this is really something that compares very well to the actual use case. And we hope that we can, well, in the near future, show something more impressive. Then also for those interested, quick advertisement, there are a couple of webinars coming up for also other use cases that we have. So you might check out our website, quantumsimulations.de/events. It's free, you can register, you can go from everywhere, you can join from everywhere. So just if you're interested. Thanks.